Hello there people, Weston here, and this is TIS-100. It is a simulator of parallel programming in assembly. This description usually elicits one of two reactions. The first is from a group of people who look at it and think to themselves, oh, this is too difficult, this is too complicated, this is too unfamiliar, I don't want to have anything to do with this. The second is from people who look at it and think to themselves, this is complicated, this is difficult, I know exactly what it is, it's all too familiar, I don't want to have anything to do with it if I'm not getting paid to do it. These people are probably IT professionals, they deal with programming on a daily basis and they don't find it as appealing as a hobby since they already do it professionally. The first group of people are obviously people who have not been exposed to programming all that much and do not feel like being exposed to it via a game. There is a third group, of which I am a member, which reacts with both understanding and enthusiasm. It's a group of people who, as was succinctly expressed in a post on GOG, would agree with the statement, coding is fun. And I believe this is the sort of approach that is necessary for you to enjoy this game in the slightest. If you do not believe that coding is fun, if you do not believe that crafting a set of instructions for a computer to obey is something that would excite you in the slightest, that these mental puzzles and gymnastics necessary to perform certain practical functions via a mechanical electronic proxy of a computer are fun, then this might not be the game for you and this might not be the LP for you. And there are plenty of others out there that you may be a lot more excited to watch and maybe a lot more entertained by. If that hasn't scared you off, then keep listening because I will explain to you as clearly as I possibly can all the concepts involved in this game, all the knowledge necessary for you to understand the problems I will be facing and the solutions I will come up with. There is no easy way of doing this, and I understand that listening to this may be somewhat tedious, but understanding the concepts involved before you see my solutions and my explanations of those solutions may enhance your enjoyment greatly. If you are dedicated enough to want to watch the LP, which will be quite long, be dedicated enough to listen to the explanations first, as you will be able to catch my train of thought, sustain it, and predict where I will go next, what I will type in next, and what will happen next. And that's one of the most satisfying experiences in watching an LP of a puzzle game, is if you can figure things out for yourself before the person showing you the solution does so, isn't it? At least in my eyes. Before we delve into programming concepts, I wanted to give you a brief introduction of the game's story. It mostly stays out of the way, you can ignore it, and it probably will not affect your enjoyment of the game if all you want to do is solve puzzles, but it exists in this game, and since I'm the sort of person who enjoys both storytelling and puzzles, I figured I would be remiss not to acquaint you with this brief introduction that you have right in front of your eyes right now. It is a simple letter that reads M, which presumably is the name of the protagonist here. It is not completely filled out for whatever reason. I assume that the original letter features the full name and is just abbreviated here in its presentation, though we cannot necessarily be sure. Either way, M. We are all still in shock here from Uncle Randy's sudden passing. While we wait on word from the examiner about the cause, we are coping as best we can. I've been occupying myself sorting through his things, especially his computers. Of course, I took one look in the garage and it all looks like a bunch of junk to me. I'll send some pictures when I get a chance. For now, this is the machine that was set up on his workbench when he died. Maybe you'll be able to figure out what he was doing with it. He would have liked to know someone was going to finish his work. Love, Aunt Doris. This may seem largely unremarkable, but there are a few things here which raise suspicion and pique interest. The computer in front of which the protagonist is allegedly seated used to belong to his Uncle Randy. Uncle Randy is dead. Uncle Randy has died suddenly and in a mysterious fashion. He has died of unknown causes. Interestingly enough, the last thing he was occupying himself with was this particular computer, and now we are in front of it. Doesn't sound like the best of ideas, does it? Doesn't sound all that smart, but hey, we can solve the mystery, at least to an extent. At the very least, we'll be able to see what he was doing, won't we? Conceivably. Now let's get down to details. The Tessellated Intelligence System is a parallel computer. It is comprised of nodes, mostly basic execution nodes, BENs. So far, since you don't know what a basic execution node is, let's represent it by a black box. And now let's fill in some information about this basic execution node. What does it have and what can it do? What it has are, first of all, two registers. A register is simply something that can store a value. Only one of these registers can be accessed directly, and that's the accumulator. The second register can store a value, but only for certain operations, as I will explain later. What this basic execution node can do is execute commands. You can input up to 15 commands to a given node. They will loop around, as once again I will explain later. To summarize, the basic execution node has two registers, the accumulator and the backup register. It can store up to 15 lines of code, up to 15 micro operations. And one more thing, it can communicate with the other nodes, because as I mentioned, it is a parallel system. Not every node can communicate with every other node. These nodes are organized in a particular fashion. This is usually called the topology. You may find many fancy terms for many fancy things around here, but the basic idea is that they are somehow connected, and they are probably connected based on how they are put in space, and the connection used here is very, very basic. Let me show it to you. At most you have 12 nodes at your disposal aligned in a grid. 4 horizontally, 3 vertically. A node can contact any of its neighbors orthogonally, meaning up, down, left, right, but not diagonally. To do so, it uses so-called ports. The functionality of a port is very simple. You can write to a port and then the value arrives at that port, and then you can read from that port, at which point the value will be taken from that port and put in the destination node. It's as simple as that. What exactly happens to that value is determined by the operation for which the destination node uses that value. Another thing to keep in mind is that if you are to process values, you probably take them from someplace and output them to someplace else. This can be as simple as getting a value from a port at an edge node and outputting it to a port on some other edge node, but you can have multiple inputs and in fact multiple outputs. Now that you have the basics down, let me consolidate that knowledge and expand upon it with the explanations I have been doing live. This will be a lot more systematic and thorough, but on its own it might have lacked the clarity. That's why I chose to present a tiny introduction beforehand. Either way, here goes. All registers store integer values between -999 and 999 inclusive. Alright, so it's symmetrical, which is weird because the negative value usually is, well, never mind that. These are weird values we are discussing here. How many values is that? Well, no, I guess it makes sense. It's 1,999 values. That seems weird enough. What sort of numerical system is that supposed to work on? Well, never mind. All right. It works on integers. Integers from -999 to +999. Not 666, but 999. There might be a story behind this game. The representation of register values is implementation defined, and knowledge of the representation is not required to program the basic execution node. These people are answering the questions I am asking. Of course, my initial question was, well, what sort of representation is there? It doesn't seem like something that would work well in binary. And they're like, don't worry about it. It's implementation defined. All you need to know is right here. ACK, which is accumulator, of course. Type internal description. ACK is the primary storage register for the basic execution. Of course, the accumulator. Results of things should go to the accumulator, right? Accumulator is used. Yes, of course. Yes, That's how it works. It's like it's absolutely like assembly. Accumulator is used as the implicit source or destination operand of many instructions, including arithmetic and conditional instructions. Brilliant! Back, internal non-addressable. Back is a temporary storage for values in accumulator. It is only accessible through sav and swap instructions, cannot be read or written directly. We have nil, which is internal special. Reading nil produces the value 0, so it's like /dev/null or something. Nil can be used as a destination operand to execute an instruction for its side effects, only discarding the brilliant. So you can write to nil, to not actually write to anything, if you want the results to go nowhere, and you can read 0 from nil if you want a 0. Want a 0? Go to nil. It has plenty. Left, right, up, down. Type port. The 4 communication registers up, down, left, right correspond to 4 ports that all basic execution nodes use to communicate with topologically adjacent nodes. Some ports will be disconnected and so the nodes within the hardware. That's so fancy. That's so goddamn fancy, but look at it. It's just a fancy expression, and yet you have them arranged in a 2D grid. The fact that some of them may be disconnected just means that in some places you don't actually have anything connected to the up port or the left port because you are, for instance, in the top left corner, so nothing is connected. Obviously. Because it cannot, because you're in a corner. I mean, they could have made a donut out of it. It's a perfectly fine topology. Any pseudoport. When any is used as the source of an instruction, the instruction will read the first value that becomes available on any port. When any is used as the destination of an instruction, the result of the instruction will be sent to the first node that reads from any port on this machine. This is important. This is the architecture. This is what we have. We have a number of registers and a few ports. Okay, that's all we have. We have the accumulator, the backup for the accumulator, the nil register, which only has zeros and you can dump stuff in there, left, right, up, down registers, any register, which can be used as a source or a target, and last. Last refers to the port last read or written using any. It otherwise behaves identically to explicitly specifying a port, leading from and referring to last before it has been set by successfully read or write, will result in implementation-defined behavior. Probably failure. Well done, PastMe. Now that PastMe has explained to you what we have, namely registers and ports in all of their variety and glory, let PastMe also describe what you can do with them. Namely, let him list all the available instructions. Take it away, PastMe. You're doing a mighty fine job, if I may say so myself. Here come the instructions. Instruction set. Source and destination may refer to may specify a port or internal register. Any use of a port will block until the corresponding node connected to that port completes the communication by reading or writing a value. Additionally, source parameter may be a literal integer value. Okay, so you may define a number as source. That's okay. Back cannot be specified as source or destination. The values of back is only accessible through special instructions save and swap. A label parameters are arbitrary textual names used to specify jump targets within the program. You can have labels in this? We may have goto. All text included after the hash symbol is ignored. Text placed after 2 symbols will be used as the title of the program in which it occurs and is displayed in the debugger. Labels are used to identify targets for jump instructions. No operation, that's self-explanatory. Nope. Nope is a pseudo instruction that has no effect. Move. Move, source, destination. So move 8 ac means move the value 8 to the accumulator. Move left, right, reads the value from left, writes it to right. Move up nil takes value from up and discards it. 2 registers per node. Every node has the accumulator and the backup register. And we can perform an operation on the backup register. We can perform a swap. The values of accumulator and the backup register are exchanged. Save, the value of accumulator is written to backup. Add source. Oh, of course, so the add operation means that you add the source value or source register and place the value in the accumulator, of course. Subtract. Value is subtracted from the value in the accumulator. Neg. The value of your accumulator is arithmetically negated. The value of 0 remains the same. Jump. Transfers execution unconditionally. Of course, I know this one, so it's basically an unconditional jump. It then jumps to a label. With this operation, if the value in the accumulator is equal to 0, a jump will occur to the label. If it's not 0, a jump will occur with this. If greater than 0 will occur here. If less than 0 will occur here. This is an unconditional jump to a given instruction. Jump relative operation 2, jump skips a single instruction. Jump relative operation accumulator. Next instruction to execute will be determined by the value. Oh, this is brilliant. So you can give the value from, of course, because you cannot refer to the backup register, you can only refer to the accumulator, but you can read the value from the accumulator and then jump to the instruction based on the value in the accumulator. Nifty. Node type T30, memory stack node. Oh no! Pay no attention to my horrified reactions. It's a perfectly simple thing to understand, and if I show it to you on an example, it will be all that much simpler. A stack holds values. You can only access the values from the top of the stack. So far, our example stack is completely empty. There's nothing there. So let's put something on top of the stack. Let's put a number there. Let's put 3 there. So now we have a stack which has 3 on top. We can put something else on the stack as well. We have the 3 already. So we put something on top of the 3. We stack these values. And now the value on top is 7. You could go on and stack values on top of one another if you wanted to. However, if you want to get a value back, you remove it from the top of the stack, you return it someplace, wherever that might be, and the top of the stack becomes the value below. If we return the 3, we remove the 3 from the stack and the stack is empty, and the top is the very bottom. Once again, let's start with an empty stack. Let's put something on top of this stack, a single value. Let it be 8. So we have 8 on the stack, and it's on the top of the stack. Let's put one more value on top of the stack. This is usually called pushing. We push a value on top of the stack. Keep in mind, all the things in the stack are kept there. The fact that you can only access the top one doesn't change the fact that there can be a lot more of them there. It's just that you can only access the top one. So if we push 5 to the stack, it goes to the top. We have 8 below it and 5 above it. If we want to get the value or remove the value, we pop it. And the top of the stack is one value below it. In this case, the 8 we put before it. Understanding how a stack works isn't all that scary. The scary part is that with a stack you can do quite a few things, and therefore the puzzles will probably get quite complicated eventually. And now listen to past me discuss the very few last things mentioned in the manual, after which I hope you will enjoy the LP, because the game is quite interesting, quite nifty, quite original. You can't take that away from it. It is original. It is not the sort of experience most games provide. It is quite unique. It's quite special. I hope you'll enjoy it, but regardless of whether you do or not, have a nice day and a nice life. And they insist on vocabulary that will be barely understood by most non-technical people and will sound as fancy as possible. I mean, it's supposed to be technical documentation, so I guess that's the idea. They are supposed to be technical. Random access memory node. God damn it, we don't have RAM. You can set breakpoints. So exclamation mark for breakpoints. Sheesh. Visualization module. Of course, it doesn't have RAM memory, but it sure as hell has a visualization module. What kind of schizophrenic design this? Visual module supports the following colors: black, dark gray, bright gray, white, and red. Brilliant! It's like a movie noir.